Hello class, so this is my long-awaited video that I've been wanting to do since I started, and I apologize to everybody for not getting you a video sooner. I finally have everything I need to do it, so hopefully, Lord willing, time permitting, I will have y'all a video every week to go over what we need to go over. So chapter 18, this is 18.1, kinetic energy. There's two types of kinetic, well, there's more than two types of kinetic energy, but the two we're going to focus on is translational and rotational kinetic energy. And when we say translational, we're talking about T equals 1/2 mass times velocity. We'll say G because that's the point we're going to be looking at, squared. And just so y'all know, from my point of reference, I always put an arrow if it's a vector, let you know it's in vector. I can't do bold print like the book does, so that's my vector. This is if angular velocity, which is also a vector, equals 0. Then your kinetic energy, which we are saying is T, that's what the book says. Personally, I would have wrote E, but yeah, hey, we're going to go with what the book says, since y'all have the book. If the rotation is about a fixed axis, then T would equal 1/2 the mass times the volume plus the inertia of moment about G times the angular velocity squared. So this is if you have translation and rotational kinetic energy. 18.2 covers work of a force, which we're going to call U. So the work of a force is equal to the integral force, which is a vector, times the difference of the radius, which if you take it all the way to which direction you're going to, in the x direction, well, depending on what sign you use, would be force equal to cosine d theta, or excuse me, cosine theta ds. Now, if the force, that's for a variable force. If the force is constant, we'll say work of force constant equals the constant force cosine theta times s, which is the distance is changed. The work of weight equals negative the force of weight times delta y. So you're changing elevation, changing y, depending on where your datum is. Even though the gravitational force will be different at delta y, assume a constant gravitational force, which we all know to be negative 9.81 meters squared per second, or negative 32.2 feet per second. But just know that actually if you changing y is more than just a little bit, then you will actually have to take into account your gravitational effect. But for everything we'll be doing and everything that'll be on your test, this is appropriate. So just assume that the gravitational constant is the same. In the rotation about a fixed axis, we know that T equals, T being kinetic energy, 1/2 mass times the volume squared about the G plus 1/2 the moment of inertia about G times the angular velocity squared. since the velocity about the g equals the radius about the g times the angular velocity about the g, we can deduce that t equals 1/2 the inertia about g plus the mass times the radius of gyration about g squared times the angular velocity about g. And you might recognize this right here, this, which equals the moment of inertia. And so therefore, in some of your gradings, you see me use these 3 dots. That's a mathematical term for therefore. I have no idea what the actual name is, but therefore, the kinetic energy equals 1/2 the inertia of the rigid body times the angle velocity squared. This is important. It's coming in very important in a lot of your homework. So, because this can be represented many different ways. And so we're going to work problem 18.1. And 18.1 basically asks us to show that the kinetic equation of kinetic energy equals 1/2 the mass times the volume times the velocity about g squared plus 1/2 the moment of inertia about c times the angular velocity squared equals 1/2 the moment of inertia about c times the angular velocity squared. So we have our basic equation here. We see that Vg is equal to angular velocity times the radius. So we plug that in down here. And we see that 1/2 the mass times the angular velocity, g by c squared, plus 1/2 the inertial velocity times the angular velocity squared equals this. Well, we see that this here in the parentheses is equal to this right here, IC. Therefore, if we replace this with this, we get 1/2 the inertia times the angular velocity, and we answer what we were looking for, and that's how the math works. So 18.2 covers the work of a spring force, which we'll call U for work and S for the spring. Now we know the force of a spring is equal to the constant of the spring times S, which is going to be our distance or change in distance. So the work of a spring equals negative 1/2 the constant of the spring squared in the second position or the end position minus 1/2 K. Oh, look at there, I left out the S squared. The S in the first original position, so S squared in the original position. So this is basically all that 18.2 is. Work of the spring equals negative 1/2 the constant of the spring squared at the end position minus 1/2 of the constant of the spring in its beginning position squared. Section 2 also covers forces that do no work. These include fixed points. If they can't move, they can't do any work. Perpendicular to their displacement. So, for example, a force that doesn't do any work is friction. Friction doesn't do any work because when you apply it, it's applied to an instantaneous point, which means that the instantaneous velocity is 0. So in section 3 of chapter 18, we talk about the work of a couple moment, which we'll define as U of M, U sub M. U sub m is the integrated version of theta, where it begins, so initial theta, to where it ends, theta 2, times the moment, or from the moment to the change in theta. Now this is if it's variable. If your moment is variable, you have to integrate. If your moment is constant, you do not. It makes it a lot easier. So the work of the moment equals the moment times the end of theta minus the beginning of theta, the beginning position of theta. The end position times the beginning position. Now, it's important to remember that theta is in radians, not degrees. That's important to note. Also important to note is that a couple moment only does work if there's actual rotation involved. If it's rigid and doesn't move, there's no work. If it doesn't translate or rotate, there is no work. So section 4 covers the principle of work energy. Here we have the kinetic energy in its starting position plus the sum total of all the work done from point A to point B or 1 to 2 equals the end potential energy. Now there's a couple things you need to think about. Is when you're calculating this, the internal forces do not need to be considered because we're simply talking about if it's translational or rotational movement. So the internal forces pay nothing to this. And the initial translation, and so basically what this is saying is the initial translation or rotational kinetic energy plus the work done by outside forces and couple moments acting on a body as it moves from the initial position, which here is 1, to the final position, which here is 2, equals the body's final transitional or rotational force, kinetic energy, T2. So in section 5, we're talking about the conservation of energy. So let's first define the other form of energy. We know we have kinetic energy and potential energy. So here we've already spoken about kinetic energy. Now let's talk about the potential energy. Here Vg is going to represent our gravitational potential energy, which equals the weight times the change in y about the g, which is the center, about the center of gravity. Another type of potential energy is elastic potential energy, which is like for a spring. So if you push that spring in, it has a force to push out, which is the potential is built there to explode. So it's plus, positive, not negative like the force. The force is negative, Ks. But here, the potential energy is positive, 1/2. The constant of the spring times the distance squared. So that's our two forms of potential energy. So the total potential energy, which is V, equals the gravitational potential energy plus any elastic potential energy. We'll give you your total V. So if you remember back to chapter 14, that the sum of the work of conservative energy equals the potential energy at 1 minus the potential energy at 2. At the beginning, at the end. The potential energy at the beginning minus the potential energy at the end. Now, if we look at what we've been working on, you'll see that the potential energy, or excuse me, the kinetic energy at the beginning, plus the potential energy at the beginning, plus the sum of the non-conservative energy, which is something like friction, something that wasn't conserved in the system. You have the conservation of energy, which means beginning energy equals end energy. So non-conservative equals kinetic energy equals the kinetic energy at the end plus the potential energy at the end. Now, if this equals 0, then we know that the potential energy, or excuse me, the kinetic energy plus the potential energy in the initial position equals the kinetic energy at the end plus the potential energy at the end, which is the law of conservation of energy. All right, so let's work a problem. This is problem 12 out of chapter 18. And if you'd like to follow along in your book, it says determine the velocity of a 50 kilogram cylinder after it has descended a distance of 2 meters. Initially, the system is at rest. The reel has a mass of 25 kilograms, and the radius of gyration about its center mass A is 125 millimeters. So we're given the mass of the cylinder is 50 kilograms. As it drops, change in distance of 2 meters. The initial velocity is at rest, so it's 0. The mass of the reel is 25 kilograms. The diameter of the reel is 0.075 meters. The radius of gyration about A is 0.125 meters. And we need to determine the velocity at the end of 2 meters. So we know that it's at rest at T1, so T1 equals 0. The sum of work from point 1 to point 2 is the force cosine theta times the distance. Well, cosine theta, it's going straight up, straight down, so it's going to be 1. So force equals mass times acceleration, and then the distance. The mass is 50 kilograms. The acceleration due to velocity, 9.81 meters per second squared. The distance, 2 meters, equals 981. And since we're doing work, joules, that's our work. That's kilograms per meter squared per second squared. So we've got this one, 0. The work at 981 joules equals T2. T2 is 1/2 the moment of inertia times the angular velocity squared. Here, since we have the radius of gyration, we say I is equal to the mass times that squared. And also the angular velocity, we have to divide by the diameter of the reel, which is 0.075. So we have 1/2 the mass times the radius of gyration squared times the velocity. This is your angular velocity here squared. So that gives us a total of 25 V squared. Now let's solve for V squared. Since we know this side here is equal to 981 joules, we know this side here is 25 V squared. We can solve for V squared. Let's do it. Well, I'm sure all y'all know how to finish this up. Since I did it, I'm going to show it to you. So we have T1, sum of the work equals T2. We know that T1 is 0. Sum of the work is 981 joules. T2 is 25 V squared. Divide both sides by 25 and take the square root of both sides. So we know that V equals 981 divided by 25, which should be 405 meters per second. So that's the answer. The velocity when the 50 kilogram cylinder drops 2 meters is 4.05 meters per second. All right, I hope you're all ready for another problem. This is chapter 18, problem number 40. If you look in your book, looks like this one. So I've drawn it out right here. You'll see some of this information they give you doesn't matter. So I'll read you the problem. An automobile tire has a mass of 7 kilograms and a radius of gyration of 0.3 meters. If it is released at rest from A, here we're at A. On an incline, determine the angular velocity when it stops on the horizontal plane. Angular incline, we're going to say it stops on B. Now if you look here, they give you more information you need. We're saying B is our stopping point. So let's work the problem. We're given that the mass of the tire is 7 kilograms, the radius of gyration is 0.3 meters, there's no tire slippage. We need to determine the angular velocity. We'll set our datum at B, which we said here is the bottom of the ramp. Our velocity is equal to 0.4 times the rotational velocity. So here's our conservation of energy equation. We know that T1, it's at rest, so it has 0 kinetic energy at the time. But it has potential energy because it's up high. The potential energy is equal to the weight times the change in distance of y, which is 5 meters. So that equals 7 kilograms, the weight, the mass of the tire, times the acceleration of gravity, times the height difference, yg, which comes to a total of 343.35 joules. So T1 0, V1 343, T2 equals 1/2 the mass times the velocity squared plus 1/2 the mass times the radius of gyration squared times the angular velocity squared, which equals 1/2 7 kilograms, 0.4 angular velocity squared plus 1/2 7 kilograms times the radius of gyration, 0.3 meters squared, times the angular velocity, which gives us a total of 0.0875 angular velocity squared. So we have T1 at 0, V1 at 343.35, T2 at 0.875 omega squared, and V2, which is 0, because once it hits B or datum, there is no more potential energy, so the potential energy of the second one is 0. So we have everything except omega squared. Now we use algebra to solve the problem. So thanks to the magic of digital editing, we have T1 equals 0, V1 equals 343.35 joules, T2 equals 0.875 omega squared, V2 equals 0. To solve this, we divide both sides by 0.875, cancels out there, 0.875, and then since this is squared, square root of this equals omega. So the angular velocity equals 343.35 divided by 0.87, which gives me 19.8, we're in radians, so rads per second. All right, and that's it, 19.8 rads per second. Y'all should have already known how to done all this, but you know, hey, I'm here to help. Okay, so if you've watched any of the videos I suggested you watch, and I really strongly suggest you watch them because it gives you a different perspective on how other people see the problems. Especially since, I hope you've been watching them because I haven't been giving you videos, but now I am. So hopefully I'll continue this. Wish me luck. we're going to work problem 1851. And like I was saying, if you see the videos the other guy did, he brings up the spring door with the garage. Well, this is a spring door garage problem. And the problem reads thusly. I have a friend to thank for that word. 1851. It's a long problem, but it's a short answer, so that's good. The uniform garage door has a mass of 150 kilograms. Mass of door, 150 kilograms. And is guided along smooth tracks at its end. Smooth means no friction, so we're going to ignore friction for this problem. Lifting is done using 2 springs, each of which is attached to an anchor at bracket A. You can see the picture in your book. And to the counterbalance shaft at B and C. As the door is raised, the springs begin to unwind the shaft, thereby assisting the lift. If each spring provides a torsional moment of M equals 0.7 theta, newtons times meter, where theta is in radians, theta is always in radians when we've been doing these problems, don't forget that. Determine the angle theta 0, which is your initial theta, at which both the left wound and right wound springs should be attached so that the door is completely balanced by the springs, i.e., which means it's Latin for in other words, if you didn't know that, and e.g. is ergo, FY for example, but i.e. is in other words. When the door is in vertical position and is given a slight force upward, the springs will lift the door along the side tracks to the horizontal plane with no final angular velocity. Note the elastic potential energy of the torsional spring is V equals 1/2 K theta squared, where M equals K theta, and is K equals 0. Well, it's in here, don't worry about it. K equals 0.7. So we'll say that's good. K equals 0.7 million meters. All right. Actually, it's Newton meters. Anyway, so here we go. Let's work the problem. It's not hard, won't take long. Let's draw a free body diagram. So they're saying a garage door, which we know is shut like this. It's a vertical door. When it's open, it should be completely horizontal. The mass of the door is 150 kilograms. So if you look at your book, you'll notice that this is 3 meters, which makes this 3 meters. The center of gravity is in the center, so we'll say 1.5. 0 or 1.5. We're going to call this our datum right here. 1.5. That's what we're going to assume is our datum. So we have our equation we've been working on, conservation of energy. The potential energy at 1 when the door is down is 0. T1 equals 0. It's not moving. Not potential kinetic, I'm sorry. The kinetic energy when the door is up is 0 because it's not moving. The potential energy at 1 here is going to be 1/2 our spring constant times theta squared. We have 2 springs, so therefore it's going to be 2 times 1/2 K theta squared. If our K is 7, that's going to give us a total. These 2 are going to cancel out, so it's going to equal to 0.7 theta squared. V1 equals 0.7 theta squared. V2, so this is 0, this is 0, this is 0.7 squared, one value left. V squared equals the weight times the difference in Y. So the weight is going to be 150 times 9.8, and the difference, we said our datum is going to be 1.5, so it's going to give us 2,207.25. So now we got algebra. 0, 0. So basically, V1, which is going to be 1/2, actually, we already know what it is. It's going to be 0.7 theta squared equals 2207.25. Divide each side by 0.7. Square root it. And you got theta equals 56.15 what? Not degrees, but radians. Now, how many radians are in a circle? I hope you know that, but if you don't, 2 pi. There's 2 pi radians in a circle. So if you want to know how tight you would need to wound these springs, you would divide this by 2 pi, which will give you, I don't even need a calculator, I've already done it, 8.94 rotation turns. It needs to be turned 8.94 times in order to achieve what we're looking for here, which is a, thanks for watching.